Hey everyone, welcome to this deep dive into logistic regression. If you've ever wondered how machines make decisions, like whether an email is spam or not, or how a medical system predicts disease probability, logistic regression is one of the core techniques making it all happen. Today, we're breaking it down step by step. Whether you're new to this or already familiar, by the end of this session, you'll have a solid grasp of logistic regression and how to apply it effectively. And hey, before we jump in, make sure to follow along, subscribe if you haven't already, and let's get learning. So, what exactly is logistic regression and why is it such a big deal? Imagine you're a doctor trying to determine if a patient has a disease based on test results, or a bank trying to detect fraudulent transactions in real time. You don't need a precise number, you need a yes or no answer. That's where logistic regression comes in. It helps classify things into one category or another: sick or healthy, fraud or no fraud, spam or not spam. Now, you might be wondering, why not just use linear regression and call it a day? The problem is that linear regression deals with continuous values. It tries to predict numbers on a straight line, like house prices or sales forecasts, but when you're working with categorical decisions, a straight line approach doesn't work well. Imagine trying to fit a straight line to something that should be a clear-cut yes or no. Things get messy fast. Instead, logistic regression transforms everything into probabilities, values between 0 and 1. So we can make a classification decision. If the probability is above a certain threshold, usually 0.5, we predict yes. If it's below, we predict no. Now, how does it do this? Instead of using a straight line like linear regression, it uses something much cooler, the sigmoid function. Think of it as a squishing machine. It takes any input, whether positive or negative, and compresses it into a range between 0 and 1. This ensures our predictions always stay within a logical, interpretable range. Let's say you're at a bakery. You see a fresh batch of cookies. Are they chocolate chip or oatmeal raisin? You take a closer look, maybe even a sniff, and your brain, based on past experience, makes a prediction. Yep, that's definitely chocolate chip. That's exactly how logistic regression works. It gathers input data, analyzes the odds, and classifies the result. But here's where things get interesting. How does logistic regression actually calculate these probabilities? How do we train it to make accurate predictions? And what's this maximum likelihood thing everyone keeps talking about? That's what we're about to uncover. Stick around, because this is where it gets really powerful. Wait. I have to buy a cake in the bakery, okay? So now that we know what logistic regression does, let's take a step back and compare it to something we're all familiar with, linear regression. Both models take input data and try to predict an outcome. But here's the thing. Linear regression is all about predicting continuous values. It works great when you need a number, like estimating house prices or forecasting sales revenue. You feed in the input, and it spits out a result somewhere on a straight line. Simple, right? But what happens when you're not looking for a number, but instead a decision? Imagine you're trying to predict whether a customer will buy a product or not. Linear regression might try to tell you that this customer has a 1.2 chance of buying, while another has a 0.4 chance. Hold on, what does that even mean? A probability greater than 1? A negative probability? That makes no sense, and that's the problem. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Linear regression doesn't know how to handle classification problems. It assumes everything works on a straight line scale. And sometimes reality just doesn't work that way. That's where logistic regression comes in. Instead of predicting wild, meaningless numbers, it keeps everything neatly between 0 and 1. It does this using something called the sigmoid function. Think of it as a mathematical squishing machine that takes any value and forces it into a probability range that actually makes sense. Let's put it in simple terms. Linear regression is like a speedometer. It tells you exactly how fast something is going. Logistic regression, it's more like a traffic light. It doesn't care about your exact speed, just whether you should stop or go. And just like traffic lights keep roads from turning into chaos, logistic regression keeps classification predictions under control. But here's the real question. How does logistic regression actually decide whether to say yes or no? And why is the sigmoid function so important in making that decision? That's what we're about to uncover next, and trust me, it's where things get really interesting. So, MLE stands for Mega Level Education, the secret formula that instantly makes you a data science genius. No, not buying it? All right, fair enough. It actually stands for Maximum Likelihood Estimation, but hey, that doesn't mean it's any less powerful. Now let's get real for a second. We've established that logistic regression predicts probabilities instead of just giving us random numbers, but how does it actually learn the best probabilities? That's where maximum likelihood estimation, or MLE, comes in. Think of it like this. Imagine you're a detective. You've got a crime to solve. There's evidence all around. Fingerprints, security footage, maybe even a suspiciously half-eaten donut at the crime scene. Your job is to analyze everything and figure out which suspect is most likely guilty. You're not just making a wild guess, you're carefully piecing together the clues to arrive at the best possible conclusion. And that's exactly what MLE does. MLE is like the detective of logistic regression. It sifts through all the data, tweaking and adjusting the model's coefficients to make sure the probabilities we predict match reality as closely as possible. Instead of trying to draw a straight line through the data like linear regression does, MLE works behind the scenes, adjusting things in a way that maximizes the chance of getting correct classifications. Here's an even simpler way to think about it. Let's say you're tossing a coin and you suspect it might be biased. Instead of assuming it's a fair 50-50 split, you start tracking how many times it lands on heads versus tails. The more data you gather, the more confident you become in estimating the real probability of heads. That's exactly what MLE does. It keeps adjusting the model until the probabilities make the most sense given the data we've observed. It's kind of like playing a game of hot and cold. If our model's predictions are way off, MLE keeps adjusting the numbers, nudging us closer and closer to the most trustworthy probability estimates. And once we hit that sweet spot, our model is trained and ready to make a reliable predictions. But here's where things get really interesting. MLE isn't just a cool trick for logistic regression. It's one of the fundamental ideas used everywhere in machine learning, from neural networks to deep learning. If you can wrap your head around this, you're setting yourself up for a huge advantage in data science. Now, all of this is great, but there's still one big piece missing. We know MLE helps logistic regression calculate probabilities, but how do those probabilities actually turn into a yes or no decision? That's where the real magic happens, and trust me, you're going to love what's coming next. So, we've talked about how logistic regression predicts probabilities instead of just throwing out random numbers. We've seen that maximum likelihood estimation helps fine-tune the model. But now it's time to talk about the real game changer. The one thing that actually makes logistic regression work. Meet the sigmoid function. If logistic regression were a superhero, this would be its special power. All right, imagine you're at a party and someone hands you a plate of cookies, but you hesitate. Are they delicious chocolate chip or deceptive oatmeal raisin? You need to make a decision. So you analyze. You check the texture, maybe sniff it, take a good hard look. At some point, your brain assigns a probability, let's say 85%, sure this is chocolate chip. Based on that probability, you either eat the cookie or put it back in disappointment. That's exactly what the sigmoid function does. It takes any number and converts it into a probability between 0 and 1. No crazy values, no nonsense, just a smooth decision-making curve. Now, let's get into the actual function. Brace yourself, here it comes. S of t equals 1 divided by 1 plus e to the power of negative t. Yeah, I know. It sounds like a secret code. But let's break it down. The S of t is just the sigmoid function's output. The probability, the 1 divided by part, is what keeps everything between 0 and 1. The 1 plus e to the power of negative t is the part that controls the curve. The e is that famous mathematical constant around 2.78. It's what makes this function grow smoothly. The negative t flips the input, making sure the function behaves correctly. Now, here's what it does in simple terms. If t is a big positive number, the function outputs something close to 1. If t is a big negative number, the function outputs something close to 0. And when t is near 0, the function gives us a probability around 0.5, meaning the model isn't sure which way to go, and that's the magic of sigmoid. It helps logistic regression decide between yes or no, spam or not spam, fraud or no fraud. But there's still one big question. What do the coefficients in logistic regression actually mean? How do they impact the probability? And most importantly, how do we interpret them to make real-world decisions? That's what we're diving into next. All right, now that we understand how the sigmoid function turns numbers into probabilities, let's talk about how we actually use logistic regression in the real world. And the most common form? Binary logistic regression. So what does binary mean? Simple. It means there are only two possible outcomes. Think yes or no, spam or not spam, pass or fail, fraud or no fraud. It's like flipping a coin. There are only two sides. Let's say you work for a bank and you need to figure out whether a customer is likely to default on a loan or not. You have all sorts of information, income, credit score, spending habits, but at the end of the day, your model needs to give you a clear yes or no answer. That's exactly what binary logistic regression is designed for. Now, let's get a little deeper. Remember the sigmoid function? That's what transforms our input values into probabilities. In binary logistic regression, we take all the independent variables, things like income and credit score, and plug them into the model to produce a single number. That number goes into the sigmoid function, and boom, it gives us a probability between 0 and 1. But here's the key part. Once we get that probability, we need to set a decision threshold. Usually we pick 0.5 as the cutoff. If the probability is above 0.5, the model predicts yes, the customer is likely to default. If it's below 0.5, the model predicts no, they're not likely to default. Now, here's where it gets interesting. The coefficients in logistic regression tell us how much each factor affects the final decision. If income has a large negative coefficient, that means higher income reduces the chance of default. If debt-to-income ratio has a big positive coefficient, that means the higher it is, the more likely a customer is to default. Think of it like this. Binary logistic regression is basically a smart decision-making machine. It takes in a bunch of information, weighs the importance of each piece, and then makes the best possible prediction. But here's a twist. What if we're dealing with a problem that has more than two categories? What if instead of just yes or no, we need to predict multiple options, like classifying people into beginner, intermediate, or advanced skill levels? Well, that's a different kind of logistic regression, and trust me, you'll want to stick around for this next part. So we've mastered binary logistic regression, where the outcome is just yes or no, fraud or no fraud, pass or fail. But what if we're dealing with a problem that has more than two categories? That's where multinomial logistic regression comes in. Let's say you run a restaurant and you want to predict a customer's food preference. Instead of just yes or no, now you have multiple categories: vegetarian, non-vegetarian, and vegan. A binary logistic regression model wouldn't work here because it can only handle two choices. But multinomial logistic regression, that's built for this exact situation. Instead of just splitting things into two groups, multinomial logistic regression estimates the probability of each possible category. It doesn't just decide if a customer is vegetarian, it calculates the likelihood of them being in any of the three groups. The category with the highest probability is the one the model predicts. Here's how it works under the hood. Instead of having just one set of coefficients, like in binary logistic regression, multinomial logistic regression creates separate sets of coefficients for each category. It's like the model is running multiple binary logistic regressions at once, comparing each option to a reference category. Think of it like an election. You're choosing between three candidates. Instead of just deciding yes or no on a single candidate, you compare all three against each other and vote for the one with the highest probability of winning. That's multinomial logistic regression in action. Now, where do we actually see this in the real world? Well, everywhere. It's used in marketing to predict which product a customer is most likely to buy. It's used in healthcare to classify diseases into different risk categories. It's even used in NLP, natural language processing, to classify text into different sentiment categories, positive, neutral, or negative. But there's another type of logistic regression that's similar, yet slightly different. What if our categories had a natural order? What if instead of just three random options, the choices followed a progression, like rating a product from 1 star to 5 stars? Well, there's a special type of logistic regression just for that. And that's exactly what we're about to explore next. Let me see. We've talked about binary logistic regression, which helps us classify two outcomes like spam or not spam. Then we tackled multinomial logistic regression, which lets us predict among multiple categories, like choosing between three political parties. But what if those categories actually follow a clear order? What if we're dealing with ranked choices? That's where ordinal logistic regression steps in. Think about product reviews. If someone rates a product, they don't just pick a random category. There's a clear ranking: 1 star, 2 stars, 3 stars, 4 stars, or 5 stars. A 4-star review is better than a 2-star review, but it's not twice as good. There's a relative order here, but the difference between each category isn't necessarily equal. That's exactly why ordinal logistic regression is different from multinomial logistic regression. Let's take another example. Imagine you're conducting a customer satisfaction survey with responses like very dissatisfied, dissatisfied, neutral, satisfied, very satisfied. There's a clear progression here. Someone who picks very satisfied is obviously happier than someone who picks dissatisfied. But here's the tricky part. Ordinal logistic regression doesn't just guess a single category outright. Instead, it looks at the cumulative probability of responses. Think of it this way. Instead of predicting, will this customer be very satisfied? Ordinal logistic regression asks, what's the probability that this person is at least neutral? What's the probability that they are at least satisfied? What's the probability they are very satisfied? It stacks the probabilities in a way that respects the ranking structure. That's a huge improvement over multinomial logistic regression, which treats each category as if they were unrelated, even when they clearly follow a sequence. Now, let's talk about real-world applications. Credit scoring models use ordinal logistic regression to classify customers into risk levels: low risk, medium risk, or high risk. Medical assessments use it to categorize pain levels: mild, moderate, or severe. Educational tests use it to rank students into beginner, intermediate, and advanced categories. Here's why this matters. Most of the real-world decisions we make are not just yes or no questions. They involve ranked choices, and ordinal logistic regression helps us handle them intelligently. So now we've covered the three big types of logistic regression: binary, multinomial, and ordinal. But the big question remains, how do we actually build a logistic regression model from start to finish? What are the key steps? And how do we make sure we don't mess it up? That's exactly what we're about to break down next. Great, now that we understand the different types of logistic regression, binary, multinomial, and ordinal, it's time to put it all together. How do we actually build a logistic regression model? What steps do we need to follow to go from raw data to making predictions? Think of it like baking a cake. You don't just throw random ingredients in the oven and hope for the best. There's a process, a sequence of steps that make sure everything comes out just right. Logistic regression works the same way. Let's break it down into 4 key steps. First, we start with data preparation. This is where we collect our dataset, clean it up, and make sure it's ready for modeling. We handle missing values, remove duplicates, and, most importantly, encode categorical variables. If we have data like yes and no in our dataset, we need to convert them into numbers like 1 and 0, so the model can understand them. We also normalize or standardize numerical features so that variables like income and age don't overshadow smaller scale variables. If this step is done wrong, even the best logistic regression model will fail. Next, we move to model specification. This is where we define the dependent variable, the thing we're trying to predict, and the independent variables, the factors that influence that prediction. For example, if we're predicting whether a customer will buy a product, our dependent variable is the purchase decision, yes or no, while our independent variables might be things like age, income, and past buying behavior. Choosing the right variables is critical. If we miss an important one or include too many unnecessary ones, our model's accuracy can take a hit. Then, we enter the model fitting stage. This is where the real magic happens. We use maximum likelihood estimation, MLE, to find the best fitting coefficients for our logistic regression model. The model adjusts itself, finding the weights for each variable that maximize the likelihood of accurately predicting the outcome. Think of this like a thermostat that constantly adjusts to find the perfect room temperature. It's fine-tuning itself to make the best possible predictions. Finally, we need to evaluate the model. Just because the model is trained doesn't mean it's ready for action. We measure its performance using key metrics like accuracy, precision, recall, and the ROC curve. We might also split our dataset into a training set and a test set, ensuring that our model can generalize to new, unseen data. And if we really want to make sure our model is solid, we use cross-validation to check its robustness. Now here's the thing. Building the model is just half the battle. The real challenge is interpreting the results. What do the coefficients in logistic regression actually mean? How do we translate numbers into real-world insights? And how can we tell whether our model is truly useful? That's exactly what we're about to explore next. So we've built our logistic regression model, but now comes the real challenge, understanding what the results actually mean. Because let's be honest, if a model spits out numbers and we can't explain them, what's the point? Interpreting coefficients in logistic regression is a bit different from linear regression. In linear regression, coefficients represent how much the dependent variable changes for each unit increase in an independent variable. But in logistic regression, things work a little differently. Instead of predicting actual values, we're predicting log odds. Yeah, I know, log odds sounds like something from a statistics horror movie, but don't worry, I'll break it down. Think of the model as stacking the odds in favor of one outcome over another. A positive coefficient means that as the independent variable increases, the probability of the outcome occurring also increases. A negative coefficient means that as the independent variable increases, the probability of the outcome occurring decreases. For example, let's say we're building a model to predict whether a customer will buy a product or not. If the coefficient for income is positive, that means higher income customers are more likely to buy. If the coefficient for price sensitivity is negative, That means customers who are very price sensitive are less likely to buy. But here's the key part. Logistic regression coefficients don't tell us direct probabilities. Instead, they tell us the impact on the odds ratio. To interpret them in a more intuitive way, we exponentiate the coefficients using e to the power of the coefficient. For example, let's say our logistic regression model gives us a coefficient of 0.7 for marketing spend. If we calculate e to the power of 0.7, we get about 2.01. This means that for every unit increase in marketing spend, the odds of a customer buying the product double. Now here's where it gets even cooler. We can also calculate confidence intervals for these coefficients. If an interval doesn't include 1, we can be fairly confident that the variable has a significant impact. If it does include 1, the effect might just be statistical noise, and of course no coefficient should be interpreted alone. We always look at the big picture, how different variables interact and influence the outcome. So now we've cracked the code on how to interpret logistic regression coefficients, but how do we know if our model is actually any good? Just because we have coefficients doesn't mean the model is making accurate predictions. We need to measure how well it fits the data, and that's exactly what we're about to explore next. So we've built our logistic regression model, and we even know how to interpret the coefficients. But here's the million-dollar question. How do we know if the model is actually good? Because let's be real, just because a model gives us predictions doesn't mean they're useful. In linear regression, we use R² to measure how well the model fits the data. But in logistic regression, things work a little differently. Instead of looking at variance, we focus on how well the predicted probabilities match the actual outcomes. One of the most common ways to measure this is with goodness of fit tests. A popular one is the Hosmer-Lemshow test, which checks whether the predicted probabilities align well with the actual observed values. If the test gives us a low p-value, typically below 0.05, that means there's a big difference between the predictions and the real data, which is a red flag. But if the p-value is high, it suggests our model is making reasonable predictions. Another important concept is pseudo-R² measures. Since we can't use regular R² in logistic regression, we use alternatives like Cox and Snell R² or Nagelkerke R². These give us an idea of how much of the variability in the outcome is explained by our model. While they don't work exactly like regular R², they still give us a sense of whether our model is capturing useful patterns. But here's the thing, numbers alone don't tell the whole story. A model can fit the training data really well, but still fail when making predictions on new data. That's why we also use cross-validation to test how well the model generalizes. This involves splitting our dataset into different parts, one for training, one for testing, to see if the model holds up under real-world conditions. And we can't forget about classification accuracy metrics like precision, recall, and the ROC curve, which we'll dive into soon. These tell us whether the model is making useful predictions or just guessing randomly. At the end of the day, a good logistic regression model isn't just about fitting the data, it's about making accurate and reliable predictions. But there's one sneaky problem that can ruin everything, and it happens more often than you'd think. It's called multicollinearity, and if we don't handle it properly, it can completely distort our model's results. And that's exactly what we're going to tackle next. We've built our logistic regression model, checked how well it fits the data, and everything looks great until we hit a sneaky problem that can completely mess up our results. It's called multicollinearity. And trust me, it's one of the biggest troublemakers in regression modeling. Now, what is multicollinearity? In simple terms, it happens when two or more independent variables in our model are highly correlated. Imagine trying to figure out whether exercise or diet has a bigger impact on weight loss, but it turns out people who eat healthy also tend to exercise more. Now, both of those variables are influencing the outcome, but they're also influencing each other. making it really hard to separate their individual effects. Why is this a problem? Because when independent variables are too closely related, it can make our logistic regression unstable. The coefficients can become wildly inflated, switch signs unexpectedly, or even become meaningless. In short, multicollinearity makes it hard to tell which variables actually matter. So how do we detect it? One of the easiest ways is by using the variance inflation factor, or VIF. VIF tells us how much one variable is predictable from the others. If a variable has a VIF greater than 5 or 10, that's a big red flag. It means that variable is too closely related to another one in the model. Another approach is the correlation matrix, where we check how strongly variables are related to each other. If we see very high correlations, like 0.8 or above, between two independent variables, that's a warning sign. Now, once we've detected multicollinearity, how do we fix it? One way is to remove one of the highly correlated variables. If two predictors are saying almost the same thing, we don't need both. Another solution is to combine the variables into a single feature. For example, if we have height and weight causing multicollinearity, we might combine them into a new variable like BMI. Finally, another approach is to use regularization techniques like L1 lasso or L2 ridge regression, which we'll talk about soon. These techniques help shrink the impact of correlated variables, reducing instability in the model. At the end of the day, logistic regression works best when each variable brings unique information to the table. If too many variables are saying the same thing, it confuses the model and weakens our predictions. But here's the real challenge. Sometimes, even if we fix multicollinearity, our model still struggles because of another major issue: imbalanced data. When one class heavily outweighs another, logistic regression can completely fail to detect patterns, and that's exactly what we're going to tackle next. Hedge, we've cleaned up our model, fixed multicollinearity, and everything should be smooth sailing, right? Not so fast. There's another huge problem that can totally throw off logistic regression: imbalanced data. What does that mean? Imagine you're building a model to detect fraudulent transactions. In a typical data set, maybe 99% of transactions are legit and only 1% are fraud. If you train a logistic regression model on this data, it might predict everything as legitimate and still be 99% accurate. But that's completely useless. We're not catching any fraud at all. That's the problem with imbalanced data. The same issue happens in medical diagnoses. If only 5% of patients in a data set have a rare disease, the model might just predict no disease for everyone because that gives it the highest accuracy. But in reality, missing those positive cases could be dangerous. So, how do we handle imbalanced data? The first trick is resampling techniques. We can either oversample the minority class, meaning we duplicate or generate more examples of the rare event, like fraud cases, or we can undersample the majority class, meaning we randomly remove some common cases to balance things out. One popular method for oversampling is SEMOTE, synthetic minority oversampling technique, which generates new synthetic examples instead of just duplicating existing ones. Another approach is cost-sensitive learning. Instead of treating all misclassifications equally, we can penalize the model more when it gets the minority class wrong. For example, in a fraud detection model, we might make false negatives, missing a fraud case, way more costly than false positives, flagging a legit transaction as fraud. This forces the model to pay more attention to the minority class. Then there's the issue of how we evaluate the model. When dealing with imbalanced data, accuracy alone is misleading. Instead, we focus on metrics like precision, recall, and the F1 score. Precision tells us how many of the positive predictions were actually correct, while recall tells us how many actual positive cases we successfully detected. And if we want a single metric to balance both, we use the F1 score, which is the harmonic mean of precision and recall. Finally, we can use ensemble methods like bagging and boosting. Algorithms like random forests and gradient boosting machines, GBMs, can help logistic regression by learning from misclassified cases and improving over multiple iterations. At the end of the day, logistic regression is powerful, but only if we train it on balanced and meaningful data. If we ignore imbalanced data, we end up with a model that looks accurate on paper but fails where it actually matters. But even when we fix imbalanced data, there's another challenge: overfitting. If our model learns the training data too well, it won't generalize to new cases. So how do we prevent that? That's exactly what we're about to explore next. So imagine this. You're at the gym and you see someone lifting way too much weight. They're straining, sweating, barely able to move, but hey, they look impressive, right? The problem is they're not actually getting stronger, they're just overloading their muscles, and by next week they'll probably be injured. That's exactly what happens when logistic regression overfits. It tries way too hard to memorize every tiny detail in the training data instead of learning useful general patterns. Sure, it might perform great on the data set it trained on, but the second you give it new data, boom, it completely fails. This is where regularization steps in. Think of it as a personal trainer for your model. Instead of letting it bulk up with unnecessary complexity, regularization keeps things in check, ensuring the model stays lean, efficient, and actually useful. Now, there are two main types of regularization used in logistic regression: L1 regularization, lasso, and L2 regularization, ridge. Let's start with L1 regularization, also called lasso, least absolute shrinkage and selection operator. Lasso works by adding a penalty to the model based on the absolute values of the coefficients. And here's the fun part. Lasso doesn't just shrink coefficients, it can actually force some coefficients to become exactly zero. That means it automatically removes less important features, like a strict coach who cuts the weakest players from the team. This makes Lasso perfect for feature selection. If you have a lot of independent variables, it helps figure out which ones actually matter and drops the useless ones. Then there's L2 regularization, also known as ridge regression. Ridge takes a slightly different approach. Instead of completely removing variables, it shrinks all the coefficients, preventing any one feature from dominating the model. Think of it like putting a limit on how much weight each feature can carry. It balances the workload so no one predictor goes overboard. This is especially useful when you have highly correlated variables, since it helps reduce multicollinearity. Now, if you're thinking, okay, but what if I want both feature selection and balanced coefficients? Well, you're in luck. There's a hybrid method called elastic net, which combines both L1 and L2 regularization to get the best of both worlds. It keeps the model lean while also preventing any one feature from overpowering the rest. So, when should you use which method? If you suspect that some variables don't really contribute much, L1 lasso is great because it can remove them entirely. If you have a situation where all variables are important but just need to be controlled, L2 ridge is your best bet. And if you can't decide, Elastic Net has your back. At the end of the day, regularization doesn't just improve accuracy, it makes your model stronger, more reliable, and better at handling new data. It ensures that your logistic regression model isn't just flexing for show, but actually performing at its best. But now that we've got our model trained and regularized, how do we actually implement it in Python? What does the code look like? That's exactly what we're going to dive into next. So we've talked a lot about how logistic regression works in theory, but now it's time for the fun part, actually building a logistic regression model in Python. Because let's be honest, knowing the math is great, but if we can't implement it, what's the point? Luckily, Python makes this process ridiculously easy. No need to write equations by hand or solve for coefficients manually. We'll be using scikit-learn, which is basically the Swiss Army knife of machine learning. First things first, we need to import our libraries. Think of this like getting all your ingredients before cooking. We'll need .pandas for handling our data set, NumPy for numerical calculations, scikit-learn for the actual logistic regression model. Once we have our tools, step 1 is loading the dataset. We can use pandas to read a CSV file and take a quick peek at the data with .head, because no one wants to train a model on messy, unfamiliar data. Next, we pre-process the data. This means handling missing values, encoding categorical variables into numbers, since logistic regression doesn't understand text labels, and standardizing numerical features if necessary. If our dataset isn't cleaned properly, even the best machine learning model won't save us. Then, we move on to splitting the data into training and test sets. This is crucial. If we train the model on 100% of the data, how will we know if it actually generalizes well? Typically, we split it 80% for training, 20% for testing, using train-test split from scikit-learn. Now comes the best part, training the logistic regression model. With just a few lines of code, we can create an instance of logistic regression, fit it to our training data, and it's ready to make predictions. That's right, just like that, we have a fully functioning logistic regression model. But we're not done yet. After training, we need to evaluate the model's performance. Accuracy is a good start, but we should also check precision, recall, and the F1 score to see how well the model is handling different classes. And of course, we can plot the ROC curve to visualize how well the model distinguishes between categories. Now here's the thing, just because Python makes it easy doesn't mean we can skip understanding the results. We still need to interpret the coefficients, check for multicollinearity, and possibly apply regularization if the model is overfitting. So we've built our model and evaluated it, but how do we know if it's really making the right decisions? That's where we need more advanced evaluation techniques like the confusion matrix, ROC curve, and AUC score. And guess what? That's exactly what we're covering next. Can you picture this? You're watching a crime thriller. The detective has all the evidence, the fingerprints, the motive, the surveillance footage. They've built their case. They're confident they've got the right suspect. The courtroom is silent as the verdict is read. Guilty or not guilty? But what if they got it wrong? What if they accused an innocent person? Or worse, let the real criminal walk free? That's exactly what happens when we don't properly evaluate our logistic regression model. Just because it gives us predictions doesn't mean they're right. And if we don't check its performance carefully, we could be making huge mistakes, like wrongly classifying patients in a medical diagnosis or failing to detect fraud. A lot of beginners just check accuracy and call it a day. Sounds logical, right? If the model is right most of the time, it must be good. Wrong. Accuracy can be incredibly misleading, especially when dealing with imbalanced data. Imagine a fraud detection model where 99% of transactions are normal. If the model just predicts normal every time, it's 99% accurate and completely useless. That's why we need better metrics, like precision, recall, and the F1 score. Precision tells us when the model predicts fraud, how often is it actually correct? Recall tells us, out of all the actual fraud cases, how many did the model successfully catch? F1 score is the balance between both, because in real-world applications, we often have to trade off between catching as many positive cases as possible and minimizing false alarms. But numbers alone aren't enough. We need visual proof. That's where the ROC curve comes in. The ROC curve, receiver operating characteristic curve, is like a lie detector test for your model. It plots the true positive rate against the false positive rate at different threshold settings, showing us how well the model separates positive and negative cases. The further the curve is from the diagonal, random guessing, the better. And then we have the AUC score, area under the curve. If AUC is 0.5, your model is basically flipping a coin. If it's close to 1, your model is a mastermind perfectly ranking predictions. But what if the results aren't great? What if our model is struggling? That's when we ask the tough questions. Is it overfitting? Are we missing key variables? Do we need to rebalance the data or adjust the probability threshold? Because here's the truth. A logistic regression model is only as good as its real-world performance. And speaking of real-world problems, there are some classic mistakes that can ruin even a well-trained model. And trust me, you'll want to know about them before they happen. Okay, now imagine this. You're at an airport security checkpoint. The X-ray scanner is buzzing, and the security officer has to make a split-second decision. Is this bag suspicious or not? Get it right, and they prevent a dangerous situation. Get it wrong, and either an innocent passenger is pulled aside for no reason, or worse, a real threat gets through. This is exactly the kind of trade-off our logistic regression model faces when making predictions. And to measure how well it's doing, we turn to one of the most powerful evaluation tools in machine learning, the ROC curve and AUC score. Let's start with the ROC curve, short for Receiver Operating Characteristic Curve. Sounds fancy, but here's what it actually does. It plots the true positive rate, sensitivity, against the false positive rate at different threshold levels. In simple terms, it shows us how well our model separates the positive and negative cases. Picture this. If our model is perfect, it will correctly identify all positive cases while keeping false positives at 0. That would give us an ROC curve that hugs the top left corner of the graph. If the model is just randomly guessing, the curve falls along the diagonal line, meaning it has 0 real predictive power. And that's where AUC, area under the curve score, comes in. AUC is a single number that summarizes the entire ROC curve. Here's how to interpret it. If AUC is 0.5, your model is basically flipping a coin. If AUC is close to 1, your model is a prediction genius, perfectly distinguishing between positive and negative cases. If AUC is below 0.5, well, you might have built a model that's worse than guessing, and it's time to go back to the drawing board. Now, here's where things get interesting. Our goal isn't always to reach an AUC of 1.0. In real-world scenarios, we sometimes intentionally adjust the threshold depending on the problem we're solving. In medical testing, we might lower the threshold to catch more true cases, even if it means some false positives. In fraud detection, we might raise the threshold to avoid too many false alarms. At the end of the day, the ROC curve and AUC score give us a clear picture of how well our model balances sensitivity and specificity. But even with this, logistic regression isn't perfect. There are common pitfalls that can completely derail even the best models. And if you want to avoid them, you'll definitely want to stick around for what's coming next. I have a new job for you. Yeah, SpaceX, please, building a spaceship. Everything looks perfect. The engines are strong, the navigation system is high-tech, and the design is flawless. But right before launch, you realize you forgot to put fuel in the tank. Suddenly, all that hard work is useless because of a tiny but critical mistake. That's exactly what happens when we make common mistakes in logistic regression. Even a well-built model can fail if we overlook key issues. Let's talk about the biggest pitfalls that can completely wreck a logistic regression model and how to avoid them. I have a new job for you, Ami. Please. Building a spaceship. Everything looks perfect. The engines are strong, the navigation system is high-tech, and the design is flawless. But right before launch, you realize you forgot to put fuel in the tank. Suddenly, all that hard work is useless because of a tiny but critical mistake. That's exactly what happens when we make common mistakes in logistic regression. Even a well-built model can fail if we overlook key issues. Let's talk about the biggest pitfalls that can completely wreck a logistic regression model and how to avoid them. I have a new job for you. You're now a chef at a world-class restaurant. Your mission? Create the perfect dish. You gather the best ingredients, use top-quality spices, and follow the recipe exactly. You serve it to your customers, expecting a round of applause. Instead, they spit it out. Turns out, you forgot to cook it. That's exactly what happens when we make common mistakes in logistic regression. You can have the perfect dataset, the right variables, and even great accuracy, but if you overlook key details, your model might be completely useless in the real world. Logistic regression is powerful, but it's also easy to mess up. Let's go over the biggest pitfalls that can wreck your model, and more importantly, how to avoid them. First up, ignoring multicollinearity. This happens when two or more independent variables are too closely related, making the model struggle to figure out which one actually matters. Imagine listening to two people telling the same story at the same time. It just creates noise. If multicollinearity is present, the model's coefficients become unstable, sometimes even flipping signs. The fix? Use a variance inflation factor (VIF) test to spot these variables, then either remove or combine them. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Next, overfitting. This is like a student who memorizes every past exam question but has no idea how to apply the knowledge. An overfit model performs amazingly on training data, but falls apart when faced with new, unseen data. The solution? Use regularization techniques like lasso, L1, and ridge L2 to prevent the model from becoming too complex, and always validate it using cross-validation. Then we have failing to check assumptions. Logistic regression assumes that independent variables have a linear relationship with the log odds of the outcome. But what if they don't? The model's predictions won't make sense. That's why visualizing the data first is so important. Never assume the relationship is there without checking. And here's a big one: misinterpreting coefficients. Unlike linear regression, logistic regression coefficients don't tell us a direct increase or decrease in the outcome. Instead, they affect log odds, which isn't always intuitive. If you misinterpret these numbers, you might make bad business decisions. The trick? Exponentiate the coefficients to convert them into odds ratios. This makes them actually useful. But the biggest mistake? Relying only on accuracy. In imbalanced datasets, like fraud detection or medical diagnosis, accuracy is a trap. If 99% of transactions are legitimate, a model that just predicts not fraud will have 99% accuracy, but will be totally useless. Instead, use precision, recall, F1 score, and the ROC curve to measure real performance. At the end of the day, logistic regression is a fantastic tool, but only if used correctly. Avoid these mistakes, and you'll have a model that is accurate, reliable, and actually useful in the real world. Now, we've covered the fundamentals, the pitfalls, and the key techniques. But what if you want to go beyond basic logistic regression? What if you want to apply more advanced methods to make your model even better? All right, so you've mastered the basics of logistic regression. You've built models, avoided common pitfalls, and evaluated performance like a pro. But now it's time to level up. Because here's the thing. Real-world problems aren't textbook problems. The data sets are messy, the relationships between variables aren't always simple, and sometimes standard logistic regression just doesn't cut it. That's where we step into the world of advanced techniques. First up, interaction terms. In traditional logistic regression, we assume each independent variable affects the outcome individually. But what if two variables work together to influence the result? For example, imagine we're predicting customer churn, and we find that low income increases the risk, and poor customer support increases the risk. But when both happen together, the effect is far worse. That's an interaction effect. And by adding interaction terms to our model, we can capture these hidden relationships. Next, handling nonlinearity. Logistic regression assumes a linear relationship between independent variables and the log odds of the outcome. But in real life, that's often not true. Sometimes a variable's effect is curved or has threshold effects. One way to fix this is by adding polynomial terms or using splines, which allow us to model more complex relationships while still keeping the logistic regression framework intact. Now let's talk about mixed effects models. In some cases, our data isn't just a simple table, there are grouped structures hidden inside. For example, if we're studying student performance, the data is clustered by school, and each school might have different factors affecting students. A standard logistic regression model would ignore this, but mixed effects models allow us to account for these grouped relationships. And then there's Bayesian logistic regression. Traditional logistic regression estimates coefficients using maximum likelihood estimation, MLE, but Bayesian methods take a probabilistic approach, incorporating prior knowledge to improve predictions. This is especially useful in small data sets or cases where we want to incorporate domain expertise into the model. Finally, let's talk about ensemble methods. While logistic regression is great, sometimes combining it with other models can supercharge performance. Techniques like bagging, boosting, and stacking can improve logistic regression's predictive power. For example, using gradient boosting on top of logistic regression can help capture nonlinear patterns that logistic regression alone might miss. At the end of the day, logistic regression is more than just a simple classification tool. It's a gateway to more powerful modeling techniques. And when you start adding advanced methods like interactions, nonlinearity, mixed effects, Bayesian techniques, and ensembles, you unlock a whole new level of predictive power. Now, we've talked theory, we've talked advanced techniques, but nothing beats a real-world case study. How does logistic regression actually make an impact in business, healthcare, and beyond? Let's take everything we've learned so far and apply it to a real-world problem, one where getting the right prediction can literally save lives. Imagine you're a data scientist at a hospital, and your job is to build a model that predicts whether a patient has a malignant tumor or a benign tumor based on different medical features, things like tumor size, patient age, and family history. This isn't just some theoretical math problem. Doctors will use your model to make real medical decisions. No pressure, right? Here's how we approach it using logistic regression. First, we collect the dataset. In this case, we're working with 1,000 patient records, each containing features like tumor size, patient age, cell shape uniformity, and genetic markers. The target variable, whether the tumor is malignant, 1, or benign, 0. Next, we clean and pre-process the data. This means handling missing values, encoding categorical variables like patient gender, and normalizing numerical features so that no single variable dominates the model. Then we train our logistic regression model using maximum likelihood estimation, MLE, to estimate the best fitting coefficients. The model applies the sigmoid function to transform raw predictions into probabilities, allowing us to classify patients as high risk or low risk. But here's where things get really interesting. Once we train the model, we need to interpret the results. Let's say our model finds that tumor size has the highest positive coefficient. That means larger tumors significantly increase the likelihood of malignancy. If age has a small or negative coefficient, it suggests that younger patients might have a lower risk of malignancy. If family history has a strong effect, it tells us that genetic predisposition is a key factor. By exponentiating the coefficients, we can convert them into odds ratios, helping doctors understand how much each factor increases or decreases the risk. Now here's where we face our first big challenge: imbalanced data. If only 10% of patients in our dataset have malignant tumors, our model might just predict benign every time and still achieve 90% accuracy. Useless, right? That's why we use precision, recall, and F1 score rather than just accuracy to measure the model's effectiveness. Next, we evaluate the model using the ROC curve and AUC score. If the AUC is close to 1, our model is highly effective at distinguishing between malignant and benign cases. If it's hovering around 0.5, we're basically guessing, and it's back to the drawing board. Finally, we deploy the model in a hospital setting where doctors can input a patient's test results and get a probability score of whether the tumor is malignant. This isn't just about making predictions, it's about augmenting human decision-making. Doctors still make the final call, but with logistic regression, they get an additional layer of data-driven insights. The result? Our model achieves 85% accuracy in detecting malignant tumors, helping doctors catch cancer earlier and provide better treatment. And that's the real power of logistic regression. It turns raw data into life-changing insights. But logistic regression isn't just for healthcare. What if we wanted to predict customer behavior in marketing, like whether someone will buy a product or not? Now we switch the gears. We've seen how logistic regression can save lives in healthcare, but what about the business world? What if we want to use it to predict customer behavior and boost sales? Imagine you're a data scientist at an e-commerce company, and your goal is to predict whether a customer will make a purchase after receiving a marketing email. This isn't just about curiosity. Getting this right means sending the right emails to the right people and increasing revenue without annoying customers with spam. So, how do we do it? Let's break it down. First, we collect historical customer data, maybe from the last 6 months of email campaigns. Each row in our dataset represents a customer and includes features like email open rate, time spent on the website, past purchase history, and discount offered. The target variable? Whether the customer made a purchase, 1, or didn't, 0. Next, we clean and preprocess the data. We encode categorical variables like customer location, handle missing values, and normalize numerical variables so that different scales, like website time in seconds versus purchase frequency, don't distort the model. Now, we train our logistic regression model. It learns which factors are most important in determining whether a customer will buy. And here's where things get interesting. If email open rate has a high positive coefficient, it tells us that customers who actually open the email are much more likely to purchase. If discount offered has a strong impact, it suggests that offering bigger discounts drives higher conversions, but we might need to balance that with profitability. If time spent on the website has a weak or negative coefficient, it could mean customers who browse a lot but don't buy are just window shopping. By exponentiating the coefficients, we can convert them into odds ratios, giving the marketing team actionable insights. For example, if customers who received a 20% discount are 2.5 times more likely to buy, we can optimize future promotions accordingly. Now let's talk about challenges. One major issue in marketing data: class imbalance. Maybe only 5% of customers actually make a purchase, so if we blindly predict no purchase every time, we still get 95% accuracy, but zero value. That's why we focus on precision and recall, not just accuracy. We also analyze the ROC curve and AUC score to see how well the model separates potential buyers from non-buyers. A high AUC score means we can confidently target the right customers with marketing campaigns. Finally, we deploy the model by integrating it with the company's email system. Now, instead of blasting emails to everyone, we can send personalized offers to the customers most likely to buy, increasing conversion rates by 25%. And that's the beauty of logistic regression in marketing. It turns raw customer data into real revenue growth. Now, we've seen logistic regression in healthcare and marketing, but what if we take a step back and summarize everything we've learned? We've covered a lot in this journey through logistic regression, from the basics of how it works to real-world applications in healthcare and marketing. But let's take a step back and sum it all up. At its core, logistic regression is a classification algorithm. Unlike linear regression, which predicts continuous values, logistic regression predicts probabilities and then assigns outcomes as 0 or 1 based on a threshold. It does this using the Sigmoid function, which converts any input into a probability range between 0 and 1. We then explored the different types of logistic regression, binary logistic regression for two-class problems like spam detection, multinomial logistic regression For problems with 3 or more unordered categories, like predicting customer preferences. Ordinal logistic regression for ordered categories, like rating systems or customer satisfaction levels. Then we got into the mechanics of logistic regression, how it estimates coefficients using maximum likelihood estimation, MLE, and how we interpret those coefficients using odds ratios. We also discussed key challenges like multicollinearity, imbalanced data, and overfitting, and how to fix them using regularization techniques, L1 and L2, resampling, and proper model evaluation. Speaking of evaluation, we learned that accuracy alone is misleading and that we should rely on better metrics like precision, recall, F1 score, and the ROC curve with AUC to truly measure performance. And then we leveled up, exploring advanced topics like interaction terms, handling nonlinearity, mixed effects models, Bayesian logistic regression, and ensemble methods. We saw how these techniques enhance logistic regression when standard methods aren't enough. Finally, we looked at real-world applications. In healthcare, logistic regression helps doctors predict tumor malignancy and make life-saving decisions. In marketing, it helps businesses target the right customers, increasing conversion rates and revenue. At the end of the day, logistic regression is more than just an algorithm. It's a versatile, powerful, and interpretable tool used across finance, healthcare, business, and beyond. So now the big question is, where do you take this knowledge next? Whether you're applying it in your own projects, improving your data science skills, or integrating it with other machine learning techniques, you now have the foundation to go even further. And with that, I'll leave you with this. Logistic regression isn't just about predicting outcomes, it's about making better decisions with data. So go out there, experiment, build models, and most importantly, keep learning. Thanks for joining this session, and I'll see you in the next one.